Hi, we are from Group 4. So for today's session, we are going to discuss about how we apply theory computer science for our research paper, which is NFA-based parameting for the deep backend. So we are a group of 5. We have Muhammad Noriman, Bimno Hisam, Safran bin Muhammad Sapawi, we have Muhammad Hafiz bin Karakama, me, Ahmad Faiz bin Audin, and lastly, we have Abdul Aziz bin Mabini. So introduction. So we have 3 sessions. Okay, the first session is about network security and the DPI. So the first is talk about the protect data across the networks. DPI inspect full payload not just errors. It also detects hidden threats in the traffic. So we on the second session, which is pattern matching intrusion detection. So the first, it talks about the payload match against known track signatures. The second, which is finite automata track matches character by character. The third objective, which is we're going to analyze an NFA-based API paper, and the second is going to explain the proposed algorithm. The third is evaluate performance and also the limitation, and lastly, we're going to discuss contribution of the network security.
Hi, I'm Abdul Aziz. The main problem highlighted in the research is that the deep packet inspection DPI, like open source network detection system and IDS, has become more resource extensive due to the growing amount of network traffic and threats nowadays. So software-based approaches prefer DFA as it is fast but uses excessive amount of memory, while NFA is memory efficient but requires higher throughput to handle the computational payload. TCAM, however, approach is more robust with the don't care state memory but more expensive and very power hungry to apply. So to design a pattern matching engine that maintains the memory efficiency of NFA and achieve the fast clock speeds and avoids the hardware cost and complexity, the authors propose mapping NFA-based pattern matching onto BCAM.
Okay, so hello. I will covering the theoretical core of the systems to scan the malware. The firewall compile tracks signature into non-deterministic finite automations defined by 5 tuple, as you can see in here. Okay, in this real-world application, Q represents the active memory checkpoint inside the firewall. Sigma of our alphabet consists of 256 possible bytes inside of network package, and that the system rests at initial state Q0 and waiting for data. As a packet streams in, the transition functions delta calculate the next memory stage byte by byte. If patient reach the accepting state F, it means malicious signature has been successfully detected. As you can see in the diagram, the malware signature drops and tracks shared starting character D and R. Okay. Instead of building two separate of-the automations, merge this initial state notice, and notice that the structural rule here, because of this merge, every state after Q0 now has exactly one incoming transition error. This mathematical property is vital because it eliminates the duplicate state, drastically reducing the physical memory required before we map this theory into hardware.
Good day, everyone. Today I will present Chapter 4, Application of Theory, which explain how we implement the NFA pattern matching engine in hardware. To achieve gigabyte scanning speed, the engine reads packet in window of kbyte at a time. The core of our transition engine is BCAM and the RAM memory pair. Rather than using wildcard, we concatenated the current state ID and input character to form an exact search key. The BCAM actually store the transition trigger and the RAM store the next state. This setup allows the hardware to resolve transition in a single clock cycle. Finally, we use hierarchical workflow. The first BCAM hardware acts as a pre-filter, checking only the first one of two bytes of a signature. If there's a prefix match, it offloads the packet to a software evaluator to confirm threat and reject malicious packets while letting clean traffic pass safely. Thank you very much.
Assalamualaikum, my name is Muhammad Hafiz bin Karakama and I will present the significance and discussion. So why does this paper actually matter? The core reason is that it takes something we learned in theory of computer science, the non-deterministic finite automata, or NFA, and maps it directly onto the real hardware. Each NFA state becomes one binary content addressable memory entry. That's a very clean and elegant connection between theory and practice. In terms of strengths, the numbers speak for themselves. The proposed approach uses 78% less content addressable memory, compared to the best existing ternary content addressable memory based method. It also eliminates SRAM entirely, which removes a major source of delay in the matching pipeline. And by processing 4 characters per clock cycle, it achieves 16 gigabit per second throughput, fast enough for real network environments. That said, the approach does have limitations. It currently only supports exact match string patterns, so more complex regular expressions like wildcards or bounded repetitions are not yet handled. It also requires FPGA hardware, which limits where it can be deployed. But the bigger takeaway here is this. NFA is not just a concept we study in class. It is actively running inside network security systems right now, inspecting millions of packets every second. This paper shows how to do that faster and cheaper than ever before. That's all from me. Thank you.
Is that DPI and pattern matching are essential for modern network security. The second is that the paper proposed actually NFA-based matching using PCAM instead of using TCAM. And also store states on transition, so it saves up more memory and hardware costs. And the fourth, which is about parallel processing, boosts throughput, which is multiple characters per cycle. And lastly, we have tested on Snort, ClampF parent outperform the TCAM based method. Thank you.